Folks, we're off to stoichiometry land, and we need to do example after example after example, because if anybody has any problems, this is where it's going to happen, right? Stoichiometry always seems to be the dreaded calculation of any laboratory or science course, especially in chemistry, and this is no exception. And I'm going to take my time and I'm going to work through some examples and kind of gradually build up to where you need to be. All right, so we're going to do an example, and before I do that, I have to write down a reaction. I've got to give you somewhere to go or somewhere to start, right? So we're going to start off with a reaction that's 3NO2 and H2O will give me 2HNO3 and NO. And I've got a question, and the first question is, how many moles of HNO3 could be made from 63.3 moles of NO2? All right. Well, up here, I'm relating one compound, HNO3, to another compound, NO2. The only connector that I have to do that, mole of one thing to mole of another, is this mole ratio up here at the top. So that means I need a balanced chemical reaction. I've got it. They've given it to me right here. All right, so in order to do this, I take the given 63.3 moles of NO2 over 1. Mole of NO2 on top, mole of NO2 at the bottom, and I need to go to mole of HNO3, because that's what the question wants from me. Those are the two pieces I need to connect. What numbers go there? Mole ratio. That's the only number that can go there. We see that from the roadmap from above. Mole ratio has to happen, which means the mole ratio comes from the big numbers out in front in the equation. So mole of NO2, I need to find NO2. Right here it is. Very first one in the equation. There's a big 3 out in front, so a big 3 needs to go there. And I need to relate that to HNO3. So HNO3 is right here. There's a big 2 out in front, so the big 2 goes there. So in order to calculate this answer, I'll take 63.3, and then I'll multiply by 2, and then I'll divide by 3. And I hit enter, and I get 42.2 as an answer. So I would get 42.2 moles of nitric acid, HNO3, if I used that starting amount of NO2. That's it. That's all stoichiometry is. Now, I could get fancy, and maybe I could have started off with grams. I would have forced you to go from gram to mole using formula weight, right? Or I could get fancy and say, well, I don't want moles. I want to actually weigh out something. So now that you've got your answer in mole, let's take one more step and go into gram of that stuff. Use formula weight. I could talk about molecules, and I could bring in Avogadro's number like we did before. But just intro to stoichiometry, this is all that we're going to do in the first part of this lecture series. All right, so now let me keep the same type of question, the same reaction, but change it up a little. I just want you to feel comfortable with the process, right? That's all that I'm after. So same equation, didn't change a thing, but this time, how many moles of NO could be produced from 12.3 moles of NO2? All right. It's just the process that I'm after here. That's all I want you to know. So 12.3 moles of NO2 over 1. Mole of NO2 on top, mole of NO2 on the bottom, and I need to go to mole of NO. And I can do that as long as I have a balanced equation. So NO2, I find it. There it is in the equation. First one again. There's a big 3 out in front, so a big 3 goes there. Mole of NO. I need to find just NO this time. That's it. That's the last one here on the end. There's not a number in front, but that number is understood to be a 1 if it's not present. And that's all. So 12.3 times 1 divided by 3 equals 4.1. So 4.1 moles of NO is what I would get if that's how much NO2 I started with, right? So this gives me a concept of how well I'm doing in a lab, because if I turn a lab analyst loose and I say, here's 12.3 moles of NO2, go make me some NO, and then they report me a number, I'm going to compare that number to what they've actually made, right? How much did they actually make to how much should have been there? And if they're really far off from this target, this 4.1 mole, if they're really far off from that, then they might not be a very good lab worker. And this is where the whole concept of theoretical yield and percent yield come into play, and this we'll worry about a little bit later, but this is the main goal. This is what we're after here, right? It gives me kind of a target, a threshold to meet. This is what I should be getting. How close to that number am I? Because the closer I am, the better of a lab analyst I'm going to be. I don't want to be far off from this target. If so, that's bad news, and I could be without a job next week. So please keep that in mind. All right, so now I'm going to erase that example, and I'm going to keep the same equation, just use two different things to compare against. It's all, again, all about the process here. So how many moles of water could I get, or could I need, will I need, to make 6.44 moles of HNO3? All right, no big deal. I've done this twice. I can do it again. 6.44 moles of HNO3 over 1. Bring in your next step. Mole of HNO3 on top, mole of HNO3 on the bottom, and I need to go to mole of water, H2O. I can relate those two if I have a balanced equation, and I do. So water, there it is, second one in line. There's not a number in front, so it's understood to be a 1. And then mole of HNO3. There's HNO3. There's a 2 out in front, so a 2 is going to go there. So I'm going to take 6.44, multiply by 1, divide by 2, hit enter, and that gives me a 3.22 moles of water. So if I started off with 3.22 moles of water, then I'll end up with 6.44 moles of HNO3. That's all there is. So hopefully you're feeling more and more comfortable with the concept of stoichiometry now. So we'll do one more. I'll relate two more things just so you can make sure that you've got this process down pat. Make me proud, right? All right, so the next one, how many moles of HNO3 can be formed with 7.25 moles of NO? This time I'm relating two things on the same side, and that's perfectly okay. I can do it. I told you in the beginning I can relate any two. Doesn't matter what they are. Any two can be related together. So 7.25 moles of NO is what they give me. Mole of NO on top, mole of NO on the bottom. I need to get to mole of HNO3 from the reaction. So HNO3 has a 2 in front, so a 2 goes here. And NO has a 1 in front, so a 1 goes there. So I'm going to take 7.25, multiply that by 2, and then divide by 1, which is the same number. And that gives me 14.5 moles. All right. So that's all there is from a mole to mole calculation. That's the biggest heart of stoichiometry. That's really what makes this stoichiometry and not dimensional analysis. Okay? So stoichiometry relates two things together in a reaction. Any two things will work as long as you have a balanced equation to go by. So in this very first assignment, that's what you're going to see. You're going to see a lot of these equations, and it's going to say relate this thing to this one, relate this one to this one, and that's all there is to it. And if you can do these kind of 4 examples that we've done so far, I think that you're going to be comfortable enough to go into that assignment and complete those questions. So it shouldn't take you very long. They're just one-steppers. That's really all there is to it. It's one conversion. That's it. No more needed. Now in the next video, we're going to take this topic and we're going to take another step. And that's where we're going to start bringing in grams. And we're going to start bringing in molecules maybe. And we're going to try to make these a little bit longer and a little bit more complicated. But for now, if you can do these that we've done now in the past 11 minutes, you'll be able to do the next assignment without a problem. So go ahead and attempt it before you forget everything. Get all of those answers correct. And then maybe take a break. Come back and see me tomorrow sometime. And then pick up from this stoichiometry lesson, and we're going to expand on it.